Okay guys, hello. Today I would like to give you a bit of a tutorial on the analysis of heat pump and refrigeration cycle. I would like to make a notice right now that the procedure that I'm going to demonstrate is the same in general for all tables, because I'm going to demonstrate how to calculate the cycle properties using a refrigerant table like this very one. But today I am going to walk you through specifically the table of the Hilton 175 unit, which we have here at the University of Liverpool, and this is its table. So what's different about it is the reference values that the manufacturers used when they compose the table. So if you decide to use this table with its numerical values, the results on another machine, the results would most probably be wrong. So with this said, why am I doing this? Every week I get many questions people are asking how do they actually go through the procedure of calculating enthalpies and work and heat transfers. So here I decided to give you a bit of a tutorial and actually create, or at least try to create some kind of intuition about why what we do is correct. So okay, let's actually start with what we have here. Let's start with the, okay, let's see, zoom out a bit, zoom out, we can't apparently. Okay, so never mind. What we have here is called the pH diagram. Why is it called a pH diagram? Well, because we have two properties that it depicts: the pressure on the y-axis and the enthalpy on the x-axis. So it's a pretty good depiction of the cycle, both in terms of giving its cyclic nature and in terms of providing a tool for analyzing the actual cycle. Okay, so what do we have here? Let's start by labeling a few things. Now, the first thing that I would like to mention is that this diagram has a very nice physical meaning, physical interpretation, and this means that each of the sections of the diagram corresponds to a physical component of the refrigeration machine. So here at the bottom we have the evaporator. Okay, here at the bottom we have the evaporator, which operates at some low pressure, as we can see relative to the y-axis. We have up at the top the condenser, which operates at higher pressure. We have the compressor right here. Oops, okay. We have the compressor, and here finally we have the throttle. Now every week I say that labeling the components, labeling the stations in and out of the different components is completely arbitrary, and I haven't lied, it is so. So make sure that you keep track of your labelings. So the way I prefer to do this is the following. I prefer to label the station after the evaporator, or at the evaporator inlet, as 1.1, station after the compressor as 0.2, station after the condenser as 0.3, and finally after the throttle as 0.4. Okay, so we now have these 4 points. Let's start looking into how we actually calculating enthalpies given pressures. Now, what I would like to say is that typically for laboratory purposes we tend to work with ideal cycles. What does that mean? Is that the vapor coming out of the evaporator here is lying perfectly on the saturation curve, i.e. it's a saturated vapor, what comes out of the evaporator. And here, at the condenser, we have saturated liquid. How do I know this? Well, we know that everything that lies on the red part of the curve here is a saturated liquid, everything that lies on the rest of the curve, the pencil part, is a saturated vapor. Now, how are these incorrect in practice? Is that for practical considerations, the vapor coming out of the evaporator is slightly superheated, i.e. it lies somewhere here, the enthalpy of the vapor, and the liquid coming out of the condenser is slightly subcooled, i.e. lying somewhere here. Okay, but for purposes of simplicity, we will use points 1 and 3 being exactly on the saturation curve. The third and very important assumption is that we're dealing with an isentropic or ideal process, and let me show you what this means. I have here another diagram, which is the TS or TS diagram. It's entropy versus temperature. Again, the labelings are exactly the same. I will just put a shorthand abbreviations for all of them. Now, what that means is that here in the ideal cycle, we're dealing with this kind of behavior here. We're assuming that the entropy from the evaporator outlet through the compressor to the compressor outlet does not change, which you know in practice is impossible, but it's an important and good simplification. We will account for it in a little while. So let's go back to the HP diagram. Now, what we're going to do here is jot down a few observations. Now, we would like to simplify the process as much as possible, and here we can note that the enthalpy at 3 and the enthalpy at 4 are going to be exactly the same. This is the isenthalpic expansion process here. So we only need to calculate enthalpy at 3. Don't be mistaken and try to calculate the enthalpy at 4, because here what we have is a liquid vapor mixture which does not lie on the on saturation curve anymore, and hence it does not exhibit nice properties allowing us to calculate from steam tables, from saturated superheated tables. So what we're going to do in practice is calculate number 1, enthalpy at number 1, calculate enthalpy at number 3, which will give us enthalpy at number 4, and then calculate the two enthalpies, and you will see the isentropic enthalpy and the non-isentropic or real enthalpy here at the outlet of the compressor. Okay, so with this in mind, I would like to walk you quickly through the table that we have here. So you will notice that it says refrigerant R134a. That is the refrigerant that flows through the machine. What we have here are a few columns that I would like to draw your attention to. We have saturation temperature. You see the small s here, TS. The pressure in bar, the volume of the vapor refrigerant. We have fluid enthalpy. I choose to see this as fluid because it reminds me more of a liquid. Otherwise, you know, the fluid is both gas and liquid. But this is the column of the table that corresponds to the liquid phase of the refrigerant. This is the one that corresponds to the gas or vapor state. Again, here we have entropy for liquid state, and entropy for gas or vapor state. Now, what we have here, as you can notice here, we have been dealing with saturated values only. Okay, now here what we have is superheat. What superheat means is that these values are taken relative to the saturation temperature. So our table provides two superheated values, superheat by 10 Kelvin, superheat by 20 Kelvin. This is good because we rarely exceed 20 Kelvin, but if we do, we will see how to account for this. Now, I have a small example here, which I have obviously pre-prepared. Now, these are a set of measurements or mock-up measurements from the laboratory unit, and let me show you what they mean. So, P1 is the evaporator pressure, or the pressure at evaporator level. P2 is pressure after compressor. P3 is pressure after condenser. P4 is pressure after throttle. And as you can see here, these are exactly, so let's see, P1 I said is after evaporator, yeah. P2 after compressor, yeah. P3 after condenser, as we can see the pressure stays the same, nothing changes. P4 after throttle, the pressures drop down to the level that it was before, or 1 bar. So these are in bar. Okay, the temperatures are as follow: 21, 54, 20.5, minus 31 degrees. Now, I would like to mention this. For the purpose of this calculation, we only need temperature T2. Okay, so don't be mistaken, we don't need anything else as temperatures. Okay, every other value or every other point of this cycle will be analyzed via the pressure. Okay, so let's begin. Let's see, how do we do this? Let's see. So here we have our table. So let's have a look. We have our table. Okay, now we know, let's start with P1. We know that our P1 here is 1 bar. Okay, 1 bar. And we also know for a fact, judging by this diagram, that the phase of the refrigerant at point 1 is saturated vapor. So that immediately means two things. First, we're gonna go to the saturated values here, and we're going to select the column which deals with vapor, Hg. Okay, so if you can notice here, if you can see this table, we don't have exactly 1 bar. Okay, we have 0.8435 and 0.10637 bar. So what we have to do in this case is interpolate between these two values. What we're going to do is linear interpolation, because this is our best guess of the behavior of the process. So how do we do linear interpolation? Let's see. Okay, so the formula for linear interpolation is the following: y, or the unknown value, is equal to the unknown value of the dependent variable is equal to the unknown value, is equal to the low value of the dependent variable plus the high value of the dependent variable minus the low value times by the value of interest of the independent variable minus the low value of the independent variable over the high value of the independent minus the low value of the independent. Now, if you go through the maths, you will see that this is nothing other than the gradient of a line and the intercept of a line jotted around a bit. So I'm not going to go through the derivation of this, so we'll just accept this formula. So let's put star here for value of interest. Okay, so now all we need to do is we need to identify the low and the high values. So our value of interest here is, we said, 1 bar. So our low value is 0.8435. High value is this 1.0637. Now, obviously, I've done the calculations beforehand, and what this comes to be is, if we track these two lines here, we see that they correspond to enthalpies there, and we expect the enthalpy at 1 bar to be somewhere between these two values, and fair enough, there you go. The enthalpy is 382.47, which is closer to this one, as 1 is closer to this value. Okay, this is 1 point done. So let's take this. Okay, now let's see the other easy point. So this one is done. This one is done. The other easy point was here, 3. It lies precisely on the saturation curve, so we can just say, okay, let's use the saturated tables. Okay, so for point 3, which is the station after the condenser, let's look at our table with values. We have point 3 at 6 bar. Okay, point 3 at 6 bar. We go to our saturation table again, or our refrigerant table again, and we look for 6 bar. We don't have 6 bar, however we have 6.65 and 5.71. And as you might have already guessed, we're going to use these two values as the boundary values, or the surrounding values in this formula. Okay, so drop my prop here. Okay, so let's trace them to what? To HF. Okay, now this time we're dealing with liquids, so we're not looking at this column, we're looking at this column. Okay, HF. Right, so we expect to see something between 227 and 234 roughly, and when we plug the numbers in here, this is what comes out. You can check for yourself. H3 is 229. Yeah, let's see, 229 is between 227 and 234. Yeah, so 229 kilojoules per kilogram is what we have here. So we can take this out. Now here comes the nice part. You get one value for free, which is the enthalpy after the throttle. This is because the process is enthalpic, and what happens here is that the enthalpy doesn't change, so we can just calculate the enthalpy at 3 and say, okay, I'm gonna be cheeky, and I'm gonna take this for free, and that's my value. So as you can see, H4 here, I've put the exact same value as H3. Okay, tick. Now this is the easy part. Now let's go and cover a slightly trickier bit, which is the one where we have to deal with superheated gases or superheated vapors. As you can see, this point does not lie on the saturation curve anymore, and there is nothing that can give us this value for free. So we're going to make use of the other diagram here, and we're going to note that S1 here is precisely equal to S2. Okay, so S1 equals S2, and we need to remember this. Okay, S1 equals S2. Now S1 is equal to S2, as we said here, and we need to remember that. Now what we can do then is we can obtain S1 since it is on the saturation curve. So it's perfectly valid to use the saturation tables. There you go. We come here. We see that for a pressure of 1 bar, we can interpolate using the simple linear interpolation formula that I've given before here. By substituting the appropriate parameters for the appropriate values, we get something right in between of these two values. And I've done this ahead of time, and obviously it is, yeah, it is 1747 is between 175 and 1745. Okay, so we know that the entropy at S1 right here is 1.747. Now what we can see also at this diagram is that S2 is superheated. That means that it is not going to be trivial to calculate its properties. So what we can do though is we can say, okay, I know that the entropy at S2 is equal to that of S1, and we write this down as the same value. Now if we go ahead and try to calculate the entropy after the compressor as if it was saturated gas, judging from this column, we see that we obtain something between 1.717 and 1.758. So from the real numbers we can conclude that this is quite a long way off from the true value. So what we can do then is we can say, okay, we now know that the gas is superheated, but we don't know by how much. So what we can do is we can calculate three values of entropy. So we already calculated the saturated value of entropy at 6 bar. We can calculate the superheated value of entropy by 10 Kelvin and the superheated by 20 Kelvin. Okay, so this part of the table gives you the properties of the gas when it is superheated by 10 and 20 Kelvin respectively. And sure enough, you obtain three properties: S saturated, which we already concluded is too low, S at 10 Kelvin, S at 20 Kelvin. Now if we look at S at 10 Kelvin, we'll see that this is too high. And this is good for us because that provides us with bounds for our old friend the interpolation here. So we can again substitute the appropriate values and we can obtain the function or the property of interest that goes with this entropy S2. But what is this property? You might ask. Well, this is H2S. That's what we're trying to obtain. We're trying to find the enthalpy at point 2. Okay, so when we interpolate here, we can save ourselves some time, and instead of just interpolating here and here and here, we can also interpolate here, here, and well, and we did this. Oh, sorry, and here. Okay, so what that gives us is again three values of enthalpy, and I have written these two down as well. So from the three regions we obtain saturated enthalpy at H2, enthalpy at H2 when the gas is superheated by 10 Kelvin, and when the gas is superheated by 20 Kelvin also bears an enthalpy value. So now we can plug in the enthalpy here for the for Y and the entropy for X. So what we are interested in is the enthalpy, sorry, at 2S, which is going to be equal to the enthalpy at, now we need to apply some observation, some judgment here. We see that our real value of entropy lies between the saturated value of entropy and 10 Kelvin. So we don't need 20 Kelvin entropy at all, 20 Kelvin superheated. Okay, so what we're going to say is H2S is equal to H2 at 10 Kelvin plus H2 at 20 Kelvin minus H2 at 10 Kelvin. And now here comes entropy. S2 here, we know this, there you go, we know the value S2, S2 minus, and we use the appropriate values, S2 at 10 Kelvin over S2 at 20 Kelvin, sorry, no, S2 and saturated in 10, there you go, I got distracted, S2 at 10 minus S2 saturated. Okay, now this is S2, let's just put S1, because this is in fact S1, we obtained this from S1. Okay, now once we run this calculation, we obtain a value of enthalpy, which in actual fact lies, so the first time we obtained something that lies between here, here, and here, and now we are interested in these two, so we're going to obtain something that lies between them in this dimension. So this is called bilinear interpolation. Okay, and I have got this value as 419.74 kilojoules per kilogram. Okay, now the only thing that we are left with is this entropy here. So we've calculated the entropy at 2s. Now we need to calculate the entropy at the actual outlet of the compressor 2. So how do we do this? Now we can no longer, if we go back to our temperature entropy diagram, we can no longer use the assumption that S1 and S2 are equal, because obviously for the real process here they are not. So we'll have to resort to our temperature readings, and I said in the beginning that this is the only time that we need to use temperature. Okay, so what we do is fairly simple. We go back to our value of pressure, and this time we interpolate to the left. Okay, we interpolate to the left. Why do we do this? We do this because we know that our pressure is at 6 bar, and if it was saturated, the temperature would have lied between 20 and 25 degrees Celsius. Okay, this is very important, it's in degrees Celsius. Okay, and actually the precise value is 21.51554 degrees by just doing the interpolation.
How are you getting on all right?
By just doing the interpolation.
I'll look up the far end and I'll walk back then. Okay.
Yeah. Okay, so what we have to do then is, once we've obtained the interpolation, the saturated temperature at T2 there, what we can do is we can say, wait a minute, we know that our actual temperature is 54 degrees Celsius and our saturated temperature is 21 degrees Celsius. That means there's quite a massive discrepancy here. So we can obtain this value of 32 degrees Celsius of superheat. Okay, and luckily what this table here allows us to do is to track precisely this superheat. There you go. This is the actual temperature minus the saturated temperature. Okay, so we know that our difference between the two is 32 Celsius or Kelvin. It doesn't matter because they go degree for degree. So let's take this as Kelvin, because we have 10 Kelvin, 20 Kelvin, we have Kelvin in the table. So let's take this as 32 Kelvin of superheat. Now what we need to do then is we need to say, okay, so we know how to interpolate, we know how to find the enthalpy at 10 Kelvin superheat for 6 bar. We already did here. We know how to find the enthalpy at 20 Kelvin. But now we know that our superheat actually lies somewhere here outside of the table. It's 32 Kelvin. Well, that is not a problem, because since we're assuming linear interpolation, what we're actually saying is we know the values at these 2 points. Okay, they're spanned by a line. And because this line goes on forever and ever and ever until infinity, we can say, well, whether I'm interested in a point here or a point here, the exact same rule is going to apply. Okay, so we just use the appropriate values of x's and y's in the formula, and even though we have an extrapolation, this is called extrapolation, this is going to work perfectly fine. Okay, so we do just that. We find the enthalpy here and enthalpy here, and we come out with 2 values of enthalpy. We did before. There you go, 420 kilojoules per kilogram, 430 kilojoules per kilogram. Now what we need to say in this formula here, there you go, I'll write it out for you. Now we say, okay, the enthalpy, the actual enthalpy, is equal to the low value of enthalpy, because we're dealing with now we're dealing with no superheat. So the actual enthalpy is equal to the enthalpy at 10 Kelvin superheat plus the enthalpy at 20 Kelvin superheat minus that at 10, okay, nothing fancy, times, now look what we do here, we do times the temperature of superheat that we've just obtained, now minus one of our data points is 10 Kelvin, now minus 10, and on the bottom we have 20 because our other data point is 20 Kelvin, 20 minus 10, and this comes out to be right here 442. I actually made a typo here, so 442 kilojoules per kilogram. So we have done the scary H2 and the scary H2S, we have done H3, H4 and all that it goes with it. You see it's quite a lengthy calculation, but it is worth nonetheless. Now I'm not going to go through all the calculations for heat and work transfer because these are trivial. You just plug in the numbers that we've just obtained together into the formulas provided to you and you end up with these three values. And the same for efficiency, compressor efficiency eta, and coefficients of performance for refrigerator and heat pump respectively. Okay guys, this was all from me, and greetings from the University of Liverpool.